Here's a question for you to think about. Why do astronauts become weightless in space? Now, the common misconception is that there is no gravity out in space, but we know that that's not true. This whole part of the unit has been talking about the fact that there is, in fact, a force of gravity out in space. It's the reason why all of our planets are in orbit around the sun. It's the reason why the sun is in orbit around the center of the universe. So what's happening here? Why do these astronauts seem to feel weightless? Well, it's in the word feeling weightless. Yes, they feel weightless, and when we talk about how we feel, we're talking about our normal force. So these astronauts, as they are out in the International Space Station, feel no normal force. They do still feel a force of gravity, just no normal force. So we've looked at this in depth, something going through the air that has no normal force. I mean, that's really just a projectile. So why do these astronauts seem to float weightlessly? Well, it's because they're acting just like a projectile. They are in free fall. The astronauts are in free fall around the Earth. Now, Newton thought about this a long time ago, and he devised this thing called a thought experiment called Newton's cannon. So let's imagine that we have the Earth. And on the Earth, we have a gigantic cannon. So maybe it would look something like that with a nice opening for our bowling ball or whatever projectile we want. Now, we know that if we shoot a cannon, that bowling ball will try to fall in that parabolic path down to Earth. But if we project that bowling ball so fast, well, by the time that the bowling ball is falling back down to Earth, the Earth's curvature is causing the Earth to fall away from it. And ta-da! We suddenly have circled the Earth. And that's exactly what the process is when we think about how can we get something to go out in space, whether it be a satellite, an astronaut, anything like that. The path that they are taking is just like a projectile. Okay? And again, we're moving so fast that by the time that we are curving towards the Earth, right, the curvature of the Earth goes away. Now, let's try to think about how an astronaut might feel when they are out there in space. Now, it is true, astronauts do have a slightly smaller force of gravity than they do on Earth because they are farther away from the center of the Earth, but they don't feel weightless. Okay, when we talk about feeling, we're talking about apparent weight, and we know apparent weight is our normal force. So just to remind ourselves that apparent weight is the same thing as normal force, let's do a quick little exercise and see how somebody might feel if they are perhaps shot out of a cannon. So exercise 4 is a 70-kilogram man is shot out of a cannon at 4 meters per second squared. How heavy does the man feel? So this cannon is being shot straight up, right? And we've got this guy, he is inside, and he is going to be shot out of that cannon. Now, if we draw a force diagram for our man, right, so we'll give him a little dotted line, we would see that the force diagram would have a force of gravity down, but then we would have to have some kind of a normal force causing him to accelerate up. So if we write a net force equation for this, we would say F net is equal to the normal force minus the force of gravity. Now, if you recall from Unit 5, we also know that F net is equal to ma, so we could almost write this as ma is equal to the normal force minus the force of gravity. So our mass is 70 kilograms, so we'll put in 70 kilograms. Our acceleration is 4 meters per second squared. That has to equal the normal force minus the equation for the force of gravity, 9.8 newtons per kilogram times mass of 70 kilograms. And if you do the algebra for this, we find that the normal force for this guy is 966 newtons. So he's feeling quite a bit heavier than normal. Now, the reason why we want to think about how astronauts feel is because it would be pretty uncomfortable to feel weightless all the time. You know, your body really doesn't work very well without that force of gravity. Liquids, not liquids, but I should say fluids inside of you can redistribute, and it affects your body system. So for example, your blood and phlegm and all those other kinds of fluids in your body, they are used to being kind of pulled down towards your feet. So you've got these very strong veins going back to your heart, slightly less strong arteries going down to your feet. Now, when you go to space and you are weightless, suddenly there is no this force pulling down on these fluids, so your fluids start to redistribute and your center of mass of your body actually moves up, and I think I've read that it was 2 liters go into the upper half of your body. It also causes facial swelling. It makes people look a little weird when they're out there in space. So we don't really want to be weightless all the time. So instead, the way that we can get a little bit of artificial gravity for these astronauts so that they feel like how they feel back on Earth is to try to get the space station to spin. Now, we will look at a cylindrical space station with a 115-meter radius rotating around a longitudinal axis at a speed of 33.58 meters per second. Let's try to see what kind of artificial gravity, as demonstrated by the centripetal acceleration, we are creating here. So we know that centripetal acceleration is equal to v squared over r. So since they give us a v of 33.58 meters per second, we can just square that and divide it by the 115-meter radius. And when you put that into your calculator, you see that the centripetal acceleration is 9.8 meters per second squared. Now, why do you think we're doing this? Well, it's to exactly mimic gravity on the surface of the Earth. The surface of the Earth has an acceleration due to gravity of 9.8 meters per second squared. So by causing a space station to rotate in that particular way, we're mimicking how the people would feel on Earth. Now, lastly, we've got a nice little shorthand way of referring to how many times greater the normal force is acting on you than normal. So if you are feeling a normal force that is twice as big as normal, it means that you feel twice as heavy. If you have a normal force of 0, well, then you feel weightless. And so we like to refer to these things as G's. Okay? Really, when we calculate G's, again, all we're doing is we are taking our normal force and we are dividing it by the force of gravity. So this is what they mean when they say space is 0 G's. It's because your normal force in space would be 0, and so 0 divided by force of gravity is just 0 G's. Upon takeoff in a rocket, you feel an average of 3 G's. So your normal force is 3 times bigger than your force of gravity, and you feel 3 times heavier than normal. Now, to prepare for this, astronauts get into what is called the vomit comet, where the vomit comet goes in a sinusoidal flight path, where part of that path will make them feel heavier than normal, right? 1.8 G's. And then part of that path will make them feel weightless, 0 G's. And it's to help them prepare for how they might feel when they go out into space. Because you got to figure out how to use your body differently when you are experiencing different G's.